Welcome to Complex Analysis. Today, we are going to explore Cauchy's residue theorem. This is arguably one of the most powerful and beautiful shortcuts in all of mathematics, turning impossible calculus problems into simple algebra. Before we dive into the math, imagine a security guard assessing a fenced-in junkyard. Instead of walking every inch of the long, winding fence to look for trouble, the guard simply walks inside and counts the actual troublemakers. Each troublemaker gets a threat score based on how dangerous they are. The total threat level is just the sum of these individual scores multiplied by a standard security factor. Cauchy's residue theorem works exactly like this for complex math. To find the total value of an integral around a complicated boundary, you completely ignore the boundary itself and just add up the special values of the bad points trapped inside. Now that we have the intuition, let us define our terms formally. First, an analytic function is a mathematical relationship that is smooth and continuous, with no sharp corners. Next, a simple closed contour is just a loop that connects back to itself without ever crossing its own path, much like a rubber band. An isolated singular point is a specific location where the function breaks down, like dividing by 0, but is completely surrounded by normal, well-behaved points. Finally, a residue is a specific numerical weight assigned to that singular point, representing how severely the function blows up there. This brings us to the crown jewel of complex integration, the formula itself. The theorem states that the integral of a function around a simple closed loop C is exactly equal to 2 pi I multiplied by the sum of the residues of all the singular points trapped inside that loop. The symbol sigma means we are adding up these residues from the first singular point to the last. If the number of singular points inside our loop increases, we just add more residues to our sum before multiplying by the constant 2 pi I, which comes directly from the geometry of complex circles. Before we look at the proof, let us see this formula in action with a concrete example. We want to evaluate the integral of 1 over z minus 3 around a circular path defined by the absolute value of z equals 5. Our strategy follows 3 simple steps. First, we find where the function breaks down by looking at the denominator. Setting z minus 3 equal to 0 gives us a singular point at z equals 3. This is the only place where the function is undefined, and we call it a simple pole because the exponent of the denominator is exactly 1. Now that we have our singular point, we must check if it is actually trapped inside our loop. The loop is a circle centered at the origin with a radius of 5. The distance from the origin to our point is exactly 3. Since 3 is strictly less than 5, the point is definitely inside the loop, meaning we must account for it. Because it is inside, we calculate its residue. For a simple pole, we multiply the function by the exact term causing the division by 0 and take the limit as z approaches 3. The problematic terms cancel each other out perfectly, leaving us with a residue of exactly 1. With our residue calculated, we are ready to finish the problem. We have no other singular points to worry about, so the sum of all residues inside the loop is just this single value 1. Finally, we apply Cauchy's residue theorem to get the total integral. We take our sum of residues and multiply it by the constant factor 2 pi I. The final answer is purely imaginary, 2 pi I, which is a very common and correct result in these types of problems. Let us tackle a slightly harder problem with multiple singularities. We need to evaluate a new integral, where the function has a quadratic term in the denominator, specifically z squared plus 4. The boundary for this problem is a circle centered at the imaginary unit I with a radius of 2. We will use the exact same strategy as before. First, we set the denominator to 0 and factor it. Taking the square root of a negative number yields imaginary roots. We find 2 distinct singular points for this function, 2i and negative 2i. Next, we must test both points against our boundary condition to see which ones actually fall inside our specific circle. We check their distance from the center. The first point, 2i, is at a distance of 1 from the center, so it is safely inside the circle of radius 2. The second point, negative 2i, is at a distance of 3 from the center. Because 3 is greater than 2, this second point is outside the loop and we completely ignore it. Because only one point is trapped, we only calculate the residue for the point 2i that is inside the loop. We multiply the function by the term associated with this specific pole, z minus 2i, and take the limit. The terms causing the division by 0 cancel out nicely, leaving a safe fraction. We then substitute the value of the singular point into the remaining expression. This gives us a fraction with an imaginary number in the denominator, 1 over 4i. This is the residue for our single trapped point. We are now ready to use the main theorem to finish the problem. We plug our calculated residue into Cauchy's residue theorem. We multiply the residue by the standard constant factor 2 pi I. The imaginary units in the numerator and denominator cancel each other out perfectly. The final result is a clean, real number, pi over 2. This beautifully shows how complex paths can yield real, tangible values without ever doing traditional integration. Now that we have successfully used this formula, let us understand where this magical shortcut comes from mathematically. We start with a large closed loop C that has several isolated singular points trapped inside it. According to the principle of deformation of paths, which lets us shrink loops as long as we do not cross a bad point, we can shrink our giant loop into several tiny loops. We draw one tiny loop around each individual singular point. This means the total integral around the giant outside loop is exactly equal to the sum of the integrals around all the tiny inside loops. This diagram visually explains the derivation step we just performed. You can see the large outer boundary C, which is deformed into the smaller dashed boundaries C1, C2 and C3. Each tiny loop isolates a single bad point, Z1, Z2 and Z3. Because the empty space between the large boundary and the small dashed boundaries contains no singular points, the integral through that empty space cancels out to 0. This leaves only the tiny loops around the singular points to contribute to the final answer. Returning to our mathematical sum, we now evaluate the integral around each of these tiny loops. By the very definition of a residue, which comes from fundamental properties of complex series expansions, the integral of a function around a tiny loop enclosing a single singular point is exactly equal to 2 pi I times the residue at that point. Therefore, we can replace every single tiny loop integral in our large equation with its corresponding residue multiplied by this constant. For our final step, we substitute this definition back into our large sum. Since every term now contains the constant 2 pi I, we simply factor it out. This leaves us with the sum of all the individual residues inside the brackets. This gives the final result, the elegant form of Cauchy's residue theorem. We have proven that by focusing only on the points that truly matter, we can bypass complex integration entirely. We have covered the full topic of Cauchy's residue theorem. Let us review the key takeaways. First, this theorem allows us to evaluate complex integrals simply by looking inside the boundary, ignoring the path itself. Second, only the singular points trapped inside the loop matter. Anything outside is ignored. Finally, the integral is always 2 pi I times the sum of those enclosed residues. This beautiful theorem turns terrifying calculus into simple algebra, making it an essential tool for engineers and physicists worldwide. Great job following along.